This next unit takes a step into geometry, and it's not quite geometry in the same sense of that you dealt with in high school. We're going to be mostly talking about a lot of definitions. This first section's very definition happy and just has a few couple types of problems that you'll see. But more so the focus is going to be on shapes. So dealing with triangles, special types of them, rectangles. Then we'll jump into 3D and we'll talk about areas and volumes and surface areas of a lot of different figures. So our first section kind of deals with just one-dimensional and a creep into two-dimensional things. So we're going to be talking about points, lines, planes, and angles. So the very first thing we're going to do is we're going to talk about just lines in general and all the different kind of specific smaller types of lines that we have. So we're going to go through the name, a picture of what that looks like, and then the notation. And you're going to see that we're going to be able to use those operations of intersection and union to be able to talk about figures as well. So if you think about just a standard line, it has 2 points. That's all you need to define it, and it will continue on forever. So if I have the line AB, that means I have 1 point A and 1 point B, and the line runs through them and takes every other point as well. There's nothing that's going to be missing. And then clearly we can't say that this goes on forever, so we always use those arrows on the end to indicate keep on going. So notationally what we do is we say, okay, A and B are the 2 points that define the line, and then to indicate it's a line, we literally draw the same shape above it, okay? If we talk about a half line, anytime you think of half, it's really half of a normal line. So instead of continuing on forever in both directions, you're going to continue in one direction forever. Now there is a slight distinction because half line and ray are very similar to each other. The main difference is I'm going to be able to equal 1 point on one and not on the other. So if I have a half line, we're not going to be able to equal one of those points. So the way we signify that is with an open circle. So in this case, since my half line is AB, it means I'm starting at A and heading in B's direction. So A is the one that I'm not going to be able to equal. So we can get super close to it, which is why we need that circle there to signify it. But filled in means we actually go through that point. So A is the start, but I still don't include that on the half line. So notationally, again, I want to say I start at A and I head in B's direction, and I have a half line, so an arrow just in one direction. And then I use that open circle to indicate that I don't include this endpoint. So the distinction between that and a ray is just I can actually fill in the circle at A. So ray AB means I start at A and I head in B's direction forever. So the way I would write this notationally is the same. I just don't need to put a circle on that endpoint because I actually can equal it. If you really want to, you absolutely could put that filled in circle, but again, it's not necessary. You can just leave it off. So really only in the case that you have to exclude the endpoint would you include that circle that's not filled in. And then just for clarity, if I say ray BA, I'll still draw these points in the same direction or the same spot. Here's A and B. This means you start at B and you head in A's direction forever. So the way I would write this is, again, it's kind of backwards because it looks like my arrow is heading to the left, but I'm starting at B and I'm heading to A. So notationally, I have to put that starting point first. So any line or ray is going to have at least one side that continues on forever. The second I throw that word segment in means it's just going to cut off between those 2 points. So if I have line segment AB, just like a line, I can include these 2 endpoints, but it just connects them. We do not continue on forever. So the way I would write this is I have AB, and it's just a line segment above it, okay? Again, if you want to put these filled in circles, you absolutely can, but it's just not the typical notation. We just kind of leave them off. If I say open line segment, well, open just means the endpoints are open, so you cannot equal them, but they still define the segment. So the way we make that distinction here is it's still a line segment, so I put a bar above it, but those endpoints are open, so we put them there. If you have a half open line segment, that means one's open, one is closed. Now this doesn't really distinguish from the name which one is open or which one is closed. So it could be that A is open and B is closed. And in that case, the notation for it would be your line segment above, you have an open circle here. And now this, it kind of looks a little weird if you don't include both of them, if you just leave an open circle at one end. So we like to put the little closed circle here. But also it could be that A is closed and B is open. And in that case, the notation for that would just be the opposite. B gets the open circle, A gets the closed circle, okay? So what we're gonna do with this is we're gonna use these typical operations. What happens if I take a line and I intersect it with a ray? What do you end up getting? What about if I take a line segment and union it with a ray or union it with a line? What does it create? So we're going to try an example of this. Using this given line AD, we're going to determine the following things, okay? So the very first one, I want to take this ray, because again, you don't have a point or an open circle at the end. It means you can equal that. And I want to find the intersection. So remember this from sets. This means the intersection. So essentially what you're doing is you're figuring out what's in common or what's the overlap. Any of these are a fine way to think about what the intersection is. So all I'm going to do is I'm going to draw each of these shapes in a different color, and then I'm going to see what is the overlap. So where does the shading overlap? So starting first with ray AB. This means I'm starting at A and I'm heading in B's direction forever. So this is ray AB. Then I want to look at ray CB. That means I'm starting at C and I'm heading in B's direction forever. So if I'm looking for that overlap, this is where my shading overlaps, okay? And it includes all of these different points. So it's really the line segment starting at A and heading in C's direction. So if I take this ray and I intersect it with ray CB, A is included, C is the endpoint, and you get everything in between, okay? If you need to do separate pictures off to the side, you absolutely can do that too. But usually one picture, get some highlighters, that would help really well. And to just kind of show you maybe with some different colors, that'll work a little bit nicer. Because if I do pink and blue, then it usually overlaps to purple. So ray AB, and I'll do it above, starts at A and heads in B's direction forever. Then I've got ray CB, so that starts at C, heads in B's direction forever. And if I want what's in common, well, they both go through the point A, they both go through B, they both go through C, and you include everything in between. So you get just that line segment from A to C, okay? Let's try a second example. Now I'm gonna take a line segment AB and I'm gonna intersect it with ray CD. So starting with line segment AB, I start at A and I head in B's direction and I just get the stuff in between. So this is that line segment. And then for CD, I start at C and I head to D and I continue on forever. So if I'm looking what's in common between these two, there's absolutely no overlap. So what we would say is this results in the empty set, nothing. There is absolutely nothing in common between these two, okay? So let's give this next one a try. We will do an intersection and then we'll use the same graph to do a union as well. So starting with our first shape, we have an open circle at A. So I'm going to really exaggerate that. And I'm going to head in B's direction forever. And we can equal B. And then I start at C and I head in B's direction forever. So if I'm looking for the intersection, I need what's included in both. So if I look at these shapes, well, they definitely both go through the point C. So I'm going to shade that in. However, I'm not going to be able to shade in over here because my ray CB doesn't let me. If I look at point B, they both include that. So that's included here. And then I'm going to be able to take everything in between because they're both shaded. Same thing here, both these segments are shaded. However, when I get to point A, I can include A on the bottom figure, but it's not included on the top. So what that means is I need an open circle here at A, but we do get everything in between. So what this ends up creating is we still start at A and we head to C, and it's a line segment. I can include C, but I cannot include A, so it gets that open circle there. However, if I do the same thing, but I take the union, again, just to go through this, I start at A and I head to B, but I do not include A. Then I start at C and I head to B, and I can include both. Remember, the union means join those two together. So I meld these to one shape. So really what ends up happening is I just wanted the highlighted part. I just end up merging this right on top of the other one. And that forms one full shape. And if you see, I have no breaks in this figure at all. Everything is shaded. So this ends up creating the entire line from A to D. Okay. Now I'm just using the notation A to D because, well, that's the line they told me at the very beginning. However, you could also say this starts at A and heads in B's direction forever. You could say this is line BC. You can use any 2 points to describe that. Okay. So from here now, we're going to have a lot more just kind of definitions for a bit before we get into any examples of anything, because most of your homework is going to just be this exact kind of thing where you combine these two things together, answer some vocab questions, and then work and identify different types of angles. So before we get to angles, we're going to go ahead and talk about planes. And so a plane is just a flat surface that instead extends indefinitely in both directions. So it's very hard to indicate that it continues on forever in two directions, unlike a line. So again, we still use arrows to describe it, but it is a flat surface. So a lot of times we just draw some kind of rectangular shape. I don't know why that turned to a circle, but it did, or an ellipse. Keeps wanting to turn to an ellipse, that's fine. Let's do this instead. So I have some flat surface, but it continues on forever. So you really want to draw lines that indicate exactly that. This continues up and down forever and left and right. But really you could kind of tilt this however you want. You can kind of do something like this. It continues on forever in that direction too. What we want to talk about is what happens if we have multiple lines within the same plane, and what happens if there's multiple lines that are not in the same plane, and is there some kind of connection between the two of them. So if we have two lines in the same plane that never intersect, then we call those lines parallel lines. So just to cheat a little bit, I'm going to go ahead and take this figure again, but I'm going to get rid of the 2 lines I have in here. So if this is my plane and I have one line that goes like this, then a parallel line will run at exactly the same direction, and they will just go side by side forever. They will never cross paths. Okay? Now, what ends up happening is if you have a line in the plane, because it goes on forever in both directions, a line is always going to divide a plane into 2 different parts. And each of these parts are called half planes. So again, to use the same visual, here is my plane, and I can keep one of these lines within here. This line really divides this into 2 different pieces. There is one plane over here that ends up having a stopping boundary, but it does continue on forever in these other directions. So this piece over here is one half plane. And then likewise, we have a second plane over here that continues on forever in multiple directions, but it stops at the line. So this is another half plane. Now, if you think about the real world, we have a lot of flat surfaces, but most of our stuff is in 3D. So we talked about 2 lines that don't intersect being called parallel, but they have to lie in the same surface. However, if we have 2 lines that are not in the same plane and they still never intersect, they might not be heading in the same direction or have that same angle, but they still will never cross paths. In this case, those lines are called skew lines. And the best visual I can give you is if you think of a 3D box. So every single side of these boxes is a different plane. Okay. So the front of the box is one plane, the top of the box is another, the side of the box is another, and then you have the front, back, the bottom, all of that. So if I consider one line down here to be this edge of the box, that continues on forever. Well, another line that will never intersect it would be the line across this edge here. They will never, ever, ever cross paths, but they are in different planes completely. So one comes from the edge, one comes from the face of the box. And then our very last kind of fact with planes is if you have 2 planes intersecting, they are always going to form a line. And really you can see that directly from this. The front of the box and the bottom of the box intersect in a line. The top of the box and the side of the box form a line. So anytime you have 2 planes, which you can think of as 2 pieces of paper, whenever they get cut through each other, it is always going to form a line that continues on forever. Okay. So our last main definition or topic within this section is going to be angles, and that's really where the bulk of this section is going to come from. So an angle is formed from the union of 2 rays, and there is a common endpoint between the 2 of them. So you've seen an angle look like this. So the way we denote it is you kind of really draw that angle, and we put a little like semicircle or arc over it to indicate this is the measure that we're searching for. So you have one ray here, you have another ray here, and they share this common endpoint. So typically we like to give letters. You need a ray, so in this case ray BA, and then you have ray BC, and the point that's common to them is B. So this point is called our vertex. Okay. The actual angle is this piece right in here. There's technically 2 angles. You have another bigger one, but we like to consider the smaller one. So I'm going to call this X. Okay. So it's really a measure of, if I were to start here, how much do I need to rotate this line to get up to this end spot here? So typically this first ray is called the initial side, because we work counterclockwise with angles. And this one is called our terminal side, where that ray or the angle ends. So an angle is really formed from taking one ray, which is BA, and joining it with another ray, BC. And what it creates is an angle, and in this case, we would call this angle ABC. So you start at A, head to B, and then head to C. So B is that vertex. It should go right in the center. However, you can also label this the other way. You can start at C, head to B, and then head to A. Either one of these is a perfectly fine way to describe that angle. But again, that vertex has to go in the middle. Now, when we talk about an angle, really what we want is, what is this measure of the rotation? And there's a couple different ways you can measure it. But the measure of an angle which is denoted by just putting an M in front, is the amount of rotation from the initial side to the terminal side. And there are ultimately 3 different ways you can measure that. The most common way is degrees. So the degree of rotation to get from one side to the other. The second is radians, which is in terms of pi. And then the last angle or last measurement is in gradients. Okay. So gradients is actually really useful in engineering, and this actually comes from Europe because it's all in terms of 100ths. So every single right angle or 90-degree angle is really broken down into 100 equivalent pieces. So the angle or the measure we're going to be using to measure angles is just going to be degrees. We're not going to worry about radians or gradients. In general, if you have one full rotation around a circle, remember that's going to be 360 degrees. So for us, we're really just going to focus on an angle being smaller than that. We're not going to worry about making multiple rotations or anything of that nature. We're going to focus just on small angles. Then within here, we also have more terminology for special types of angles. So there's 4 that we're going to go through. We have right angles, acute angles, obtuse angles, and straight angles. So starting with a right angle, that means those 2 rays will form a 90-degree angle. So the way we're going to indicate that is with a little box in here. So if this is our angle X, then this angle is exactly going to be 90 degrees. An acute angle, you can think of like when you have cute tiny little animals or a cute animal, they're typically tiny. So this is going to be an angle that is smaller than 90 degrees. So again, if this is X, it's definitely bigger than 0 degrees, but it is smaller than a right angle. If you think of obtuse, usually obtuse people are kind of bullheaded or strong or big. So an obtuse angle is going to be bigger than 90 degrees. But it is going to be less than 180. So if this is our angle X, this is something bigger than 90, but less than 180. And then our very last angle is a straight angle, which means it forms a straight line. So in this case, here is our angle X. It is going to be exactly 180 degrees. So again, anytime you draw an angle, there are 2 technical measurements. There's this angle here, which is smaller, and then you have this bigger one here. Again, the measurement we like is that smaller one. Same thing with obtuse. You have this one here, and then you have the bigger angle, but it just makes sense to measure the smaller of them. 180 is typically the max we go because at that point, it really breaks that circle in half. Now, if we talk about two different angles adding up to one of these special ones, a right angle or straight angle, we have other terminology for that. So we say two angles are complementary if the sum of their measures is 90 degrees, and two angles are supplementary if the sum of their measures is 180 degrees. So we're going to try an example with this. Given this figure, we want to find the measurement of angle CBD and the measure of angle CBE. So I'm going to start with the measure of angle CBD. So that's going to be this angle right here. So if I look at the two, well, we're told this forms a right angle, so these two angles have to be complementary. So in this case, this first angle, ABC, and then the second angle, CBD, are complementary. So angle ABC and angle CBD are complementary. So if I take the measurement of angle ABC and I add the measurement of angle CBD, it should equal 90 degrees. But I know the measurement of angle ABC. They tell me it's 31. So 31 degrees plus the measurement of the angle I'm looking for must equal 90. So to solve for the angle I want, I go ahead and subtract 31 degrees from both sides. And that tells me the measure of angle CBD. I always want to do that. Is going to equal 59 degrees. Okay. So this is our first measurement. Okay. Now I also want to find the measure of angle CBE. So looking at what that is, CBE, that's this angle here. Well, CBE plus ABC forms that straight angle. So these two are supplementary. So angle ABC and angle CBE are supplementary. So if I take the measurement of angle ABC and I add the measurement of angle CBE, those have to equal 180 degrees. Okay. And again, I already know the measurement of angle ABC, that's 31. The measure of the second angle I'm looking for is still unknown. And then these have to add up to 180. So subtracting that 31 degrees tells me the measure of my other angle, CBE, is going to be 149. Okay. So the very last thing that we're going to do is we're going to talk about other special types of angles. And this is where it kind of refreshes a little bit on your high school geometry. So we're going to be talking about vert angles. We're going to be talking about if you have a parallel line cut by a third one, what kind of angles does that create, and all the different terminology for that. And then we'll do another example. So if I have two lines that are intersecting, it's always going to end up forming 4 different angles here. And what ends up happening is we create some kind of corresponding pairs. So angle 1 and angle 3 are actually going to have the same measurement. So these are called vertical angles or vert angles for short. Okay. And likewise, same thing, angles 2 and 4, they're vertically connected by one vertex. They end up having the same measurement. So we often use kind of like the arcs to indicate these are the same. And then you want to indicate, okay, these are the ones that are connected because they have one of the arcs. These two are connected because they have the two lines on them. So angles 2 and 4 are also vert angles. Now the question is, why do they end up having exactly the same measure? And really it's because you end up forming straight lines. Okay. So if I look at this, if I look at angle 1 and angle 2, those form a straight line. So the measure of angle 1 plus the measure of angle 2 will have to equal 180 degrees. But likewise, angles 1 and 4 also form a straight line. So the measure of angle 1 plus the measure of angle 4 will also equal 180 degrees. So really, if I want to find the measure of each of these things, I'm going to do 180 minus the measure of angle 1. So since you end up doing that, say angle 1 is 30 degrees, well then angle 2 is 150. But then immediately, because angle 1 is 30 degrees, angle 4 is going to be 150. So these end up having to be the same thing. And then likewise, you could do the same thing with 1 and 2, and then 2 and 3. Okay? Now, because of this, we also end up with a lot of cool stuff that happens when you have two parallel lines that are cut by a third one. So a line that intersects two parallel lines is called a transversal line. And it ends up creating a lot of equivalent angles. Because really, these two are heading in exactly the same direction. So this third line here, line 3, is that transversal line. Okay. And what you end up getting is really a clone copy of these angles because it forms in those, or hits in the same spot basically, in the same direction. So the very first types of equivalent angles we get are alternate interior angles. So if you think about these two lines with that transversal, you have 4 angles that are on the interior of the lines. And then you have 4 angles that are on the exterior of these lines. So if you think about the phrase alternate interior, this is an interior angle. The one that's on the alternate side of the transversal is 6. So angles 3 and 6 end up being exactly the same. And again, really that comes from the fact that these are clone copies of each other because this line has really just been moved down to the other since they're parallel. So if you think about your vertical lines, angles 2 and 3 are exactly the same. So when you slide those down, 6 and 7 also end up being exactly the same. So 3 and 6 must be equivalent. And then likewise, angles 4 and 5 are on the interior and they're alternate sides of the transversal. So these are exactly the same. Okay? Then kind of going hand in hand with this, you have alternate exterior angles. So in that case, if I look at this one, it's on the exterior. I go on the alternate side of the transversal, and the exterior angle corresponding to that is 8. So the measure of angle 1 ends up equaling the measure of angle 8. And then likewise, 2 and 7 end up being exactly the same. Okay. And then our final type is corresponding angles because again, you can really just slide this line down right on top of the other. these four have to be exactly the same. So corresponding means 1 and 5 are in exactly the same position. So the measure of angle 1 is equal to the measure of angle 5. 2 and 6 are in the same spots. They are corresponding. Then we've got 3 and 7. And then finally 4 and 8. But again, just because of all the vertical angles too, 1 and 4 are exactly the same, and they are exactly the same thing as 5 and 8. And likewise, 2 and 3 are vert angles, so they are equivalent, and it is exactly the same as the measure of angles 6 and 7. So we're going to do just one more example. We're going to find the remaining angles given that line 1 is parallel to line 2. So I'm told that this angle is 15 degrees, which immediately tells me that corresponding angle over here is 15 degrees. And then the other thing I can do is I can fill in this vertical angle. This has to be exactly the same. So this is also 15 degrees. And likewise, you can use the fact that this is a vertical angle or that these two are corresponding. This one is also 15 degrees. Okay. Now I need to figure out what this angle is here, and really once I have that, I have everything else. And so since 15 and this unknown angle form line 1, this angle here must be supplementary. So the way I figure it out is I take 180 degrees and I subtract 15, because the two must add up to 180. So that tells me this angle here must be 165, which again immediately tells me the angle across from that is also 165. And then over here, same thing. Because of my corresponding angles or the fact that these are supplementary at the bottom, these also must both be 165 degrees. Okay. So this gives us a start for everything. But we're gonna dive deeper into now other shapes. So working with triangles and special types, rectangles, areas, volumes, all of that kind of stuff.